Dear viewers, welcome all to LR Academy for Competitive Examinations. This time on a post on solutions on the unit solutions of Cbse curriculum standard 12th standard unit 1 creative problems which have already appeared in the public examination, that is Cbse public examination. Question number 1. Ethylene glycol is used as an antifreeze. What mass of Eg should be added to 5 kg of water to lower the freezing point to minus 5 degrees Celsius, given that Kf equal to 1.86 degrees Celsius molal? Note, Eg is a non-electrolyte. The meaning of the word non-electrolyte is it does not dissociate into cation and anion. The available data is delta Tf. Delta Tf stands for depression of freezing point, that is an addition of Eg, there is a lowering of freezing point by 5 degrees Celsius. Kf, the cryoscopic constant, is 1.86 degrees Celsius molar inverse. The first formula involved is molality small m equal to delta Tf divided by Kf, which is 5.0 degrees Celsius divided by 1.86. We get molality 2.7 molal. Now, the number of moles of Eg involved equal to N. N refers to number of moles. Molality equal to N divided by mass of the solvent. We are to calculate N. We know molality equal to 2.7. Hence, 2.7 equal to N divided by 5.00. On cross multiplication, we get the total number of moles of Eg is 13.5. We need to quantify this into grams. Hence, molecular mass of Eg equal to, that is 1 mole equal to 62 gram per mole. So, the total mass of Eg which is added to water to lower the freezing point by 5 degrees Celsius will be 13.5 multiplied by 62 gram per mole. Mole gets cancelled. So, we get 837 grams. Question number 2. Calculate the mass of non-volatile solute whose molar mass is 40 gram per mole. What should be dissolved in 114 gram of octane to reduce the vapor pressure to 80%. This is the question. Let the vapor pressure of pure octane, that is the pure solvent, be P01. Vapor pressure of octane after dissolving the non-volatile solute is 80 divided by 100 P0. Since in the question the given data is 80%. So on simplification we get 0.8 P01. Given data from the question, the molar mass of non-volatile solute is 40 gram per mole. The weight of the solvent W1, that is the pure solvent octane, is 114 gram. Hence, molar mass of octane is 114 gram. Molar mass of solute, which is represented by the formula M2, W1 mass of octane. In accordance with the relative lowering of vapor pressure by using Raoult's law, which is a colligative property, P01 minus P1 divided by P01 equal to W2 into M1 divided by M2 into W1. We know that P01 we can put 1 P01 and P1 we get the value 0.8 P01 divided by P01. So, we get a difference of 0.2 P01 divided by P01. We can cancel on the left hand side, and on the right hand side we have W2 into 114 divided by 40 into 114. We can slash off 114. So, W2 divided by 40. W2 refers to mass of the non-volatile solute. Mass of the non-volatile solute. Molar mass of non-volatile solute given is 40. And 114 in either case, that is the molar mass of non-volatile solute is also 114 and molar mass of octane is also 114. Hence, we get W2 equal to 8 gram, that is 40 into 0.2. 40 into 0.2, we get a value of 8 grams. Consider 100 milligram of protein which should be dissolved in just water to make 10 ml of solution. If this solution has an osmotic pressure of 13.3 mm rise of mercury at 25 degrees Celsius, what is the molar mass of the protein? So given data, our gas constant equal to 0.0821 liter atmosphere mole inverse Kelvin inverse. We know that 1 atm refers to 760 mm of mercury, rise of mercury. Osmotic pressure equal to, by the formula, it is also one of the colligative property, pi equal to nRT by V. N refers to number of moles, R gas constant, T temperature, V volume. Pi equal to osmotic pressure. We know that N we can use the formula Wb by Mb. Wb refers to mass of the non-volatile solute. Mb refers to molar mass of the non-volatile solute. On altering the formula pi equal to nRT by V by the inclusion of N equal to Wb by Mb, Mb equal to Wb into RT pi V. Mb refers to molar mass of the protein. Wb refers to mass of the protein. Mass of the protein in the given data, it is in milligram. We need to convert into gram, that is 0.1 gram. Hence, Mb, molar mass of the solute will be 139.80 gram mole inverse. 139.80 gram mole inverse. Now moving to the next question, we may expect another question also in this regard. Differentiate molality and molarity. Here comes a special question. What is the effect of change in temperature of a solution on molarity and molality? Molarity, capital M, is a function of temperature. At volume depends on temperature, whereas molality, small m, does not depends on temperature because its mass does not change with temperature. Only volume changes with temperature and mass does not change with temperature. Hence, m is a function of temperature, molarity, whereas molality is a non-function of temperature. Now, moving to the next question, a solution is prepared by dissolving 1.25 gram of oil of wintergreen, that is methyl salicylate, in 99 gram of benzene as a boiling point of 80.31 degrees Celsius. Determine the molar mass of the compound given Kb equal to 2.53 degrees Celsius molar inverse. The boiling point of pure benzene, that is the solvent, is 80.10. So, molar mass of solute can be calculated by the relation Mb equal to Kb. Kb refers to ebullioscopic constant or boiling point constant into Wb into 1000 divided by delta Tb, that is elevation of boiling point, 80.31 minus 80.10 into Wa, that is weight of the solvent. So Wb, the weight of the solute is 1.25 gram. Wa, the weight of the solvent is, mass of the solvent is 99 gram. Delta Tb, the difference, that is elevation of boiling point on addition of a solute, is 80.31 minus 80.10, which can be also represented as Tb naught minus Tb equal to 0.21 degrees Celsius. Kb, boiling point ebullioscopic constant, is 2.53 degrees Celsius molar inverse. On substitution of all this into the parameters of the formula, we get Mb equal to, that is the molar mass of the solute, the non-volatile solute, will be 152.11 gram. Now coming to the next question, it is an easy question. It can come as a 1 mark part in either 2 mark or 3 mark. Aquatic animals are more comfortable in cold water than in warm water. Why so? The simple answer is solubility of gases increase with the decrease of temperature. Therefore, cold water will have more dissolved oxygen. That is, in cold water, there is a decrease of temperature. And obviously, by all means, there will be more oxygen content dissolved in cold water rather than in plain water or hot water. Hence, aquatic animals will prefer to live in cold water? It's a 1 mark question which has appeared many times in the public. Now moving to the last but 2 questions of this post. Calculate the freezing point of the solution containing 60 gram of glucose. C6H12O6 is glucose whose molar mass is 180 gram per mole in 250 gram of water, that is the solvent is water. Kf freezing point constant is 1.86 Kelvin kilogram mole inverse. We know that the formula delta Tf equal to Kf into m. Delta Tf stands for depression of freezing point, Kf cryoscopic constant, that is freezing point constant, into m. Substitution of data into the formula. Kf is 1.86, W2 is 60, W1 is 250 gram, M2, that is the molar mass of glucose, is 180 gram per mole. So delta Tf equal to Kf 1.86 into 1000 into 60 divided by 180 into 250, we get 2.48 Kelvin. Freezing point depression is given by the equation delta Tf equal to Tf naught, that is freezing point of pure solvent minus freezing point of the solution on addition of the solute. 2.48 equal to 273.15 minus Tf. By altering the equation, we get Tf equal to 270.67 Kelvin. Now coming to the last question of this post. Why or measurement of osmotic pressure method is preferred for the determination of proteins and polymers macromolecules? Because osmotic pressure uses molarity, capital M, instead of molality. Hence biomolecules are not stable at high temperature and which is also poor in solubility can be easily measured. Osmotic pressure serves as a measurement even for measuring the large macromolecules or proteins or biomolecules, because osmotic pressure has an advantage. It produces a larger value even for very small rise of magnitude. Further, these biomolecules are not stable at high temperatures. Osmotic pressure measures this even at room temperature, which is an added advantage. Hence, osmotic pressure method, that is the last method under colligative property, is suitable for determining the molecular mass of biomolecules, proteins, polypeptides, and even other larger macromolecules. Thank you viewers for viewing this post. Another post will be shortly, which is also a continuation of solution. Thank you.